Today's topic we're going to be covering is cell swelling and exactly what cell swelling means and what it does. So, number one, in 2015, Brad Schoenfeld had put together almost the muscle hypertrophy Bible, right? The 3 tenements of how muscle hypertrophy traditionally has occurred that has been validated through literature. So we've seen that muscle hypertrophy or muscle protein synthesis in the fractional rate of turning over more protein due to having available nutrition, specifically amino acids, to drive the formation of new contractile units like actin and myosin, forming a new sarcomere. Structural proteins like tropomyosin and troponin, and as well proteins that are designed to help and facilitate energy production or to facilitate a mechanism for energy production, such as titin and myomesin. Regulatory protein. All of these are always undergoing protein synthesis, and one component that plays a role with that is cell swelling. So we've discussed the one yesterday, which was what we kind of did, metabolic stress, and looking at the role of lactate to a certain degree. And today we're going to basically look at the role of plasma and how, based off of the type of workload we're doing, we can influence more plasma to shift into the actual cell, the myocyte, and induce stress and have it essentially adapt and try to protect itself by undergoing more hypertrophy. So, cell swell, it's a trigger for protein synthesis. The actual muscle cell called a myocyte, when there is an increase of lactate, which we believe is one pathway, or a change of internal pressure gradient, meaning the muscles constantly being put under contraction and relax, contraction and relax, essentially pushing lines what we feel as the pump, right? We can say that the mechanical tension that induces hypertrophy, one of the 3 tenements, is directly related to mechanotransduction, or lifting a heavier weight and transmitting that information through an electrical impulse to the brain, which fires more of those high threshold motor units. The second tenement being metabolic stress, that's dictated through the increase of free hydrogen ions that are unbuffered to pyruvate, so they're not lactate yet, and how these play a role with communicating to the brain via these type 3, type 4 afferents to do the same thing that the mechanical route does, which is the end result is fire more higher threshold motor units. But then the last one appears to be more passive in nature, meaning it doesn't require the weight so much so that it requires even just a low oxygen environment will stimulate cell swelling to happen. So if we're looking at this in the scope of blood flow restriction, how does this play a role? Well, in studies that they've looked at measures of indirect markers for muscle damage, right? So if we look at some of those measures, indirect muscle damage, and why would this be important? Well, it's important to establish what blood flow restriction is doing at a mechanistic level to the muscle, because it does feel really hard to do the exercise. And mind you, if you're doing it correct, where you are using a 80% of your limb occlusion pressure for the leg. And why 80? Because studies have validated that at 80 we have the largest amount of IE and G activity. So for somebody to say, well, why not pick 78? Why not pick 79? I don't know, maybe they're trying to keep things simple and just use even numbers. But 80 appears to be a really good ceiling where we still see good blood flow into the limb. We're not having any sort of paresthesia. We are going to have some pain, but we're seeing maximum muscle contraction, and that's what we want to have happen, especially if we're at a very low mechanical load, because that's what we predict to be part of why people get stronger with BFR, even though they're using light loads. So I still want to know if I'm creating damage while I do this, because that's going to help me to establish the programming for it. You know, when we use higher weight, the programming gives us some days off, because we have done mechanistic studies that look at cytoskeletal matrix disruption or damage and how many days it takes to heal. So BFR is an exercise like high intensity. Let's see what happens. So indirect markers of muscle damage. So number one is really going to be a drop in torque production, right? So we'll say a drop in torque, right? Number two being a drop in MVC or maximal voluntary contraction, largely related to torque, but measured via EMG. Three, we're going to want to look to see if there's any sort of chronic swelling or just swelling in general. And four, obviously we're going to want to see if there's pain. So when we looked at individuals that had just completed doing a bout of exercise with blood flow restriction, we saw that there was a drop in torque production that occurred along with force production somewhere within the first 24-hour period. Now, that went right along with high intensity training, but high intensity training would continue on beyond the first 24 hours. I'm going to remove these two guys, we'll come back to them. Continued on beyond 24 hours. If here's the 1 hour afterwards, the 24-hour afterwards, 48 hour, and 72. We saw that BFR, right? If this was their baseline, they had an immediate drop within that 1 hour period, and then at the 24-hour period would come right back up to where they were. Whereas the high intensity group, right, would have a drop in torque production that would take almost about 48, if not more, hours to come back, simply because there was true cytoskeletal matrix disruption and damage which required an appropriate time of healing, which is why you can't be lifting heavy weights all the time. You do have to program this out with much detail so that one does not overreach and then overtrain. So we saw that on an indirect measure that BFR was not checking off the list on torque, decreased MVC for what the traditional models of heavyweight training gave us. Now, if we looked at pain and swelling, well, with pain, right, or reported RPE or rate of perceived exertion, we saw that if individuals were allowed to exercise all the way to a point of failure, right, let's just say a failure model, we saw that on a scale of, let's say, 0 to 10, so I do it here, we saw that BFR was really no different, right, than the other group in terms of pain. And that means that the pain basically at about the same time frame, well, within about a 24-hour period or less, came back to baseline. So there was a little blip that came up on both of these models, but came back at 24 hours, not really indicating any sort of real damage, because real damage would have continued with pain well beyond the 24 hours. That's what describes our delayed onset muscle soreness, right, beyond that period. Where they looked at the RPE scales, and obviously people rated that BFR was difficult, with the failure model being a little bit more difficult and having a bit more DOM, simply because they did just more repetitions without the BFR, because they were capable of doing that, meaning they didn't fatigue out so quick because they still had the ability to circulate nutrients in and out, or circulate free hydrogen ions in and out, allowing them to go back to the liver, or to get buffered with pyruvate to turn into lactate, to get back converted into gluconeogenesis, and all that fun stuff to just keep energy going, so they could do more than the BFR group. But we saw that pain really wasn't signifying anything that was also occurring in line with, let me check if there's questions, guys. I can't read them if there is or not. All right, if there are some questions, I'm sorry. All right, no, there aren't any. Cool. Ugh. All right, so if there aren't questions, that means I'm either talking too fast, or it's the topic is like people are just like, whoa, I've never heard that, which is fine, whatever. I'll go back later and check. But so now if we look at the fourth one, which was swelling, right? We typically would see swelling occur past the 24-hour period, right? If this was high intensity training, we would see, if here was the exercise point in time, we'd see swelling increase. We'd see it slightly increase a little bit more, and then it would start to taper off, coming back to baseline right around that traditional model of almost 48 hours later, right? Or if not a little bit more, so depending upon how hard he worked. So being as BFR was creating very similar effects to high intensity training, we thought, well, you know, does swelling play a role with this? Is it doing something like that's still following the mechanical tension model where we're disrupting tissue, creating damage, and by virtue of that, putting forward the mechanism for tissue regeneration or fractional protein synthesis, right? So we looked at BFR, and what we saw is that swelling happened very similar, but then at about the 24-hour period came down, and some individuals actually came down a little sooner than that, almost like the 10-hour period. So this did not at all look like the same type of swelling that happened with high intensity training in terms of the time frame. But when we also looked at where the swelling was occurring, right, when they looked at levels of plasma outside of the muscle and inside of the muscle, what they saw was that with BFR, with the tourniquet, there was a large influence for plasma to shift into the muscle, essentially forcing for the muscle to undergo swelling. And when that happened, the actual cells inside the muscle began to get bigger. And that myocyte, that muscle cell, because of the additional stress load that was placed on it, right? Basically, think of like a balloon getting stretched out and the walls of the balloon getting sheared. Well, the cell did what any cell would do, right? Wolff's Law. It attempted to adapt to that by making more protein structure to be able to manage with the demand. At least that's the theoretical model of why cell swelling happens. So we saw that on the indirect measure of damage, BFR wasn't creating damage. On the swelling side of things, it was inducing a type of swelling that was positively influencing protein synthesis, as far as we can make the educated assumption, because again, we're still learning how these mechanisms are occurring, and with each study uncovering a bit more, which is why, like I said in previous videos, the IRBs are becoming so difficult to do this, because they're attempting to standardize a way that we can control this in a very reproducible model, so that we have high validity and reliability in what we're doing, right? So we saw that the indirect muscle damage markers, there weren't any, none. When we looked at the direct markers for damage, so we looked at things like creatine kinase, we looked at inflammatory markers like D-dimer, we looked at things like let's see here, certain oxidative, so reactive oxygen species, or ROS. When we looked at these three factors here, we saw that with BFR, creatine kinase levels were really not all that elevated. D-dimer, not there. Reactive oxygen species, not there. So we saw that on indirect and direct measure, we weren't creating damage by applying blood flow restriction. This has been seen in multiple studies that have looked at this exact characteristic of damage. Now, the reason why I brought up damage was because the topic of today is cell swelling. And with the topic being cell swelling, we need to understand that the swelling that we're going to create and the swelling that we see in our patients, right, or clients that we're applying blood flow restriction to through a clinical model, is not going to be it's not going to indicate that we are actually creating swelling that is relevant with muscle damage. So that we can see here that we are triggering a cellular adaptive response, influencing protein turnover, influencing anabolic signaling pathways to become active, and also stimulating some other adaptive